Welcome back. Today, we are absolutely crushing two of the biggest topics on your KCNA exam, Kubernetes scheduling and the huge debate between containers and virtual machines. Look, getting these concepts down isn't just a good idea, it is non-negotiable. All right, let's get into it.
So picture this. You've got an application to deploy, right? A pod. And your cluster has 100 different nodes, 100 possible homes for it. How in the world does Kubernetes pick the one perfect spot in just a few milliseconds? Well, it's not random, that's for sure. There's a powerful algorithm at play. And trust me, it's a huge piece of the KCNA puzzle. We're going to break it down and make it super simple.
Okay, forget all that complexity for just a second. The entire secret to how Kubernetes scheduling works, it boils down to just two words: filter, then score. That is it. Seriously. Once this clicks, you'll never look at the scheduler the same way again.
So let's pull back the curtain and see what's actually happening in those two steps. By the time we're done here, you're going to understand the core logic that the Kubernetes scheduler uses every single time it places a pod. You'll see, it's actually way more intuitive than it sounds. Here it is, plain and simple. Step 1, filtering, is all about finding the nodes that could run the pod. It's about making a list of valid candidates. Then step 2, scoring, takes that list and ranks every single one of them to find the absolute best fit. Think of it as a process of elimination, followed by a talent show. Let's dig into filtering. This is the bouncer at the club. It's checking for hard requirements. First up, does this node even have enough CPU and memory? If the pod asks for 1 CPU core and the node has half a core left, nope, you're out. Next, does the pod need a specific feature, like an SSD disk? If the node doesn't have that label, sorry, you're eliminated. And finally, it checks for something called taints. We're going to cover those in a minute, but think of it as a keep out sign. If the node has one and the pod can't handle it, that node is gone from the list. Okay, now for the fun part, scoring. All the nodes that made it past the bouncer are now in the competition. The scheduler starts handing out points. A node with tons of free memory and CPU, it gets a bunch of points. A node that helps spread your applications out evenly so you don't have all your eggs in one basket, more points for you. And if you've set up some soft preferences like, I'd prefer to run in this zone, well, any node that satisfies that gets bonus points. In the end, the node with the highest score wins. That's where your pod lands. You know what? This is the best way to think about it. It's exactly like a dating app. The filtering step is you setting your absolute deal breakers. Must be a dog person, must not live 500 miles away. That gets you a list of potentials. Then, scoring is you looking at the remaining profiles and thinking, this one seems like a great fit. The one with the highest match percentage wins. If that analogy just made everything click, drop a filter score in the comments for me. So now that you know how the scheduler thinks, the real power comes from knowing how to influence it. You're not just a bystander here. Kubernetes gives you a whole set of tools to tell the scheduler exactly where you want your pods to go. The first and simplest tool you have is Node Selector. It is dead simple. You just put a label on a node, like say disk type SSD for your machines with fast storage. Then in your pod's configuration, you just say Node Selector, disk type SSD. That's it. Now the scheduler knows this pod must go on a node with that exact label. It's a hard rule, perfect for basic stuff. But what if you need something a little more sophisticated? What if you need more than a simple yes or no? Well, that's when you graduate to Node Affinity. You can think of it as Node Selector on steroids. Node Affinity gives you two flavors. First, you've got your required rules. This is a hard rule, just like Node Selector. If the rule isn't met, the pod just won't get scheduled. End of story. But then you have preferred rules. This is a soft rule. It lets you tell the scheduler, hey, I'd really like to run on a node in this zone, if possible. The scheduler will then give extra points to nodes that match, making them more likely to be picked. But if none are available, no big deal. It'll just schedule the pods somewhere else. It's flexible. And this gets even cooler. With pod affinity and anti-affinity, you're not matching node labels anymore. You're matching against the labels of other pods. So pod affinity lets you say things like, hey, make sure my web server pod runs on the same machine as my caching pod. This is great for performance. And anti-affinity is the opposite. It lets you say, make sure my primary database and my backup database never run on the same machine, which is absolutely critical for high availability. Listen up, this is a huge exam tip. You have to burn this into your brain. Node affinity is about a pod's relationship to a node. Pod affinity is about a pod's relationship to another pod. This distinction comes up on the exam Constantly, they love to test this. Okay, we've spent all this time talking about how to attract pods to certain nodes. But what if you want to do the exact opposite? What if you want to push pods away from a node? Well, for that, we have taints.
This is the key relationship you have to understand. A taint is something you put on a node, and it basically acts like a force field that repels pods. By default, nothing can get scheduled there. But if you add a matching toleration to a pod, you're giving that pod a special key that lets it pass through the force field and land on that tainted node. Now, these taints come in 3 flavors. No schedule is the most common. It just says, hey, no new pods can land here unless they have the key. Existing pods are fine. Then there's prefer no schedule, which is the soft version. The scheduler will try to avoid placing pods here, but it's not a guarantee. And then there's no execute. This one is the real heavy hitter. It not only blocks new pods, it will actively kick off any pods that are already running on the node if they don't have the right toleration.
So why on earth would you want to do this? Well, a classic example is a node with a really expensive GPU. You don't want just any random pod landing on it and wasting that resource. So you taint the GPU node. This repels all normal pods. The only pods that can land there are your special machine learning pods that you've given this specific toleration to. It's all about resource control. Okay, everybody, lean in. If you remember one thing from this section, make it this. This is a guaranteed exam question. Taints go on nodes. Tolerations go on pods. Taints repel, tolerations allow. Got it? Seriously, if that concept is crystal clear for you now, do me a favor and hit that subscribe button. All right, time for a big gear shift. We've mastered how Kubernetes schedules things. But to see the whole picture, we need to talk about what those things actually are. And that brings us to the other massive KCNA topic, the core difference between containers and virtual machines. This is ground zero for understanding the cloud-native world. Let's start with what we all used to know, the virtual machine, or VM. With a VM, you have your physical server hardware. On top of that, you install a special piece of software called a hypervisor. That hypervisor then pretends to be another piece of hardware on which you install a complete, full-fat guest operating system, another entire copy of Windows or Linux. And then finally, inside that, you run your app. It's a thick stack, which is why VMs are huge, measured in gigabytes, and take minutes to start up. The trade-off is you get really strong hardware-level isolation. Now, look at a container. The model is totally different. You have your hardware and just one host operating system. That's it. On top of that OS, you run a container runtime. And your app, with all its dependencies, runs as an isolated process that shares the kernel of the host OS. There's no guest OS, there's no hypervisor. This is why containers are unbelievably lightweight. We're talking megabytes, not gigabytes, and start up in seconds. When you put them side by side, the difference is just staggering. Startup time, minutes versus seconds. Size, gigabytes versus megabytes. Isolation, a whole separate operating system versus sharing the host kernel. And all of that leads to the biggest difference, density. On one server, you might run 10, maybe 20 VMs. On that same server, you could run hundreds, maybe even thousands of containers. That efficiency is what changed everything. And you might be wondering, what makes this all work together so well? The answer is the Open Container Initiative, or OCI. The OCI is a group that creates the rules, the open standards, for what a container image should look like and how a container runtime should behave. This is the magic that means you can build an image with Docker, and it will run perfectly on Containerd or any other runtime that follows the rules. It's the key to portability. And just like that, you did it! Congratulations! You have officially covered all the core concepts from Domain 1 of the KCNA exam, Kubernetes Fundamentals. That is a massive 46% of the entire exam done. So, what's next? We are diving headfirst into Domain 2, Container Orchestration, where we'll get deep into runtimes and security. If you are ready to knock out the rest of this thing, comment 46% done down below and make sure you're subscribed so you don't miss it. I'll see you in the next one.